Okay, thank you very much. Thank you for putting on this very nice program, giving me the opportunity to come here. And so I want to talk about specifically relativistic heavy ion collisions. It's an application to hydrodynamics. And more specifically, ways that we try to extract information from experimental data by comparing simulations to data in this framework of Bayesian inference. And then even more specifically, trying to include information about the causality or lack of causality in the hydrodynamic evolution equations in the simulations that we're doing. Yeah, and since we're talking about causality, I have to break it somewhere. I'm sure that's not the only mistake we'll find in the. Okay, so basic outline. So I don't really have all that many slides, so please feel free to ask lots and lots of questions about anything you're curious about. So I'll just kind of start with some of the basics. I don't know how familiar people are with these things. Maybe not everyone. So these are these relativistic heavy ion collisions are these experiments that are done. These are collider experiments where you take heavy nuclei is the idea. They actually collide a variety of different things, the different sizes, all the way down to protons. But the original idea is to take some very large nuclei so that when you collide them, you can hopefully start talking about macroscopic quantities like temperature and equations of state and such. So you accelerate these heavy nuclei to very high energies, let them collide, and then the system evolves. And then way at the end, you detect a bunch of debris that comes out, and you have to put together whatever you can about what happened. And so this is kind of a picture to tune here, showing kind of how we the stages involved, how we model this. The most important for this talk is that the major part of a simulation usually treats the system as a relativistic fluid, relativistic viscous fluid. But I also just want to make it clear that there's various physical processes involved. There's multiple stages, different things that can be studied, and many of them, most of them, almost all of them are things that can't necessarily be calculated reliably from first principles. So a very important part of this whole program is this kind of comparing models to experimental data to try to extract whatever information you can. So that's the context. But if you have any questions about any of the other parts of the modeling and how this works, now would be a good time to ask those. Going further, I'll just start talking about how we do this comparison to data and then the causality of the equations. But if there's anything you've ever always wanted to ask, do it now. Just to make some context or some connection to what we saw on Monday, I think, from Chun's talk. Yeah, so a lot of the topics will be the same, but in particular, this relates to what was introduced kind of on this slide, that, yeah, we have many, many different things that we would like to learn, theoretical quantities, properties of the quark-gluon plasma and other processes that happen. And we, in fact, have lots and lots of data that we can use also. But the connection between the data and the quantities that we wanted is not always very easy to see. So that's just to motivate this whole idea that, okay, we have many, many things that we don't know that we would like to know. So I want to embark on this endeavor of parameter estimation, where we want to compare calculations to experimental data to determine, values of these physical properties, but in particular, including a systematic treatment of uncertainty. So that's where this Bayesian inference comes from. So here's my one slide, the very basics of Bayesian parameter estimation. So the main goal is this parameter estimation. So the context is given some model. So it's always in context of whatever you put in. Of course, you can't treat uncertainties due to things that you don't have in your calculation at all. But given some model, what parameter values, and these parameters can be like well-defined physical parameters. They can also be sort of nuisance parameters that sort of parameterize ignorance about things that you could sort of, you want to marginalize over, or they can be physical parameters that you really want to know the values of. But what values are compatible with experimental data, and most importantly, with what precision can we determine them? And so this framework of Bayesian inference is very, very good, very useful for a detailed systematic treatment of the uncertainties in this sort of question. And yeah, so I say it's all given, it's all in the context of a model, but it's also the case that, as long as you can parameterize your ignorance somehow, you can always include it. So if your model can be a very, very broad thing with lots of parameters, then you can still say a lot about uncertainties of things that you're not certain about. Okay. And again, just stop me anytime for questions. Okay, so why Bayes? So Bayes theorem, here's where Bayes theorem comes in. So here's my treatment of Bayes theorem. So in this particular context, we'll have D and P, which are experimental data. These are measurements that have been made, and P are parameters in your model. And you start by associate each of them with probability distributions, which I think is pretty natural for experimental data. You always have uncertainties, especially statistical uncertainties are all these probabilistic things, but even systematic uncertainties you can imagine giving us some probability. So a measurement isn't just a mathematically exact value, but it's some value plus or minus some uncertainties, including possibly correlated uncertainties between different measurements. And parameters is maybe a little less obvious. Sometimes you might want to think, okay, the real world has a specific value for the mass of a pion, and that's all it is. But in reality, there's always uncertainties associated with our knowledge of these things. So it also is fairly natural that the parameters should be associated with some probability distribution that represents our confidence or our knowledge of them. So once you associate these probabilities, then you use Bayes' theorem, which is just a basic relation between conditional probabilities. So you define this conditional probability. So this likelihood is the probability. So given some values of parameters, so assuming P is true, what is the probability that D is true? So given some parameters, what is the probability that I will observe some measured data? And that particular one is called a likelihood. And Bayes' theorem is pretty straightforward. This is probably not good notation, but sort of a probability that both P and D are true can be trivially related to the conditional probabilities. So the probability of D given P times the probability of P is the same thing as the probability that P and D are true. And you can write it the other way too. So the probability of P given D times the probability of D is the same thing. So then you just solve for what you want. In this particular case, we want this posterior. So we measured some experimental data, but we don't know what the model parameter, the correct model parameters are. So we want this posterior, which is proportional to what's called the prior and the likelihood. These are the only things that depend on the parameters. So the probability of the data is just a normalization factor. All right, so there are two things that we need to do. So we need to define this probability distribution of the likelihood. So if the model predicts some value and the data gives you some value for an observable, then you need to associate a probability with that. So it should be a higher probability if they're the same, and it should be a low probability if they're different. And so this is just kind of arbitrary, but a very common thing is something that looks something like this, where this chi-squared is roughly what you think of as a chi-squared, how good it fits, and you just exponentiate the square of that. But you could put more information. So You compare, you say how different is the data to your model prediction, but you compare it to the uncertainty. And in particular, you can have an entire covariance matrix, so a matrix of uncertainties, because the uncertainty from one observable can be correlated with the uncertainty of another observable. So you take all that into account, and you throw that here, and you define this likelihood. But you also need to have this prior, so this is, well, prior knowledge that you have about the parameters, if you have any. And so that's a really nice thing about this Bayesian inference is, you have a nice natural way of putting extra information into this. So for example, if some values of parameters tend to send your simulation into an acausal regime in its hydrodynamic simulation, you can say that that's bad. I don't trust the model there, and I can reduce the probability of those, or set it to 0, which is what we will do. So that's kind of essential. The distribution of the prior, yeah, it's completely arbitrary. I mean, it's totally up to you. So what people often try to do is just try to avoid making a decision. So they take parameters and then they say that they have a uniform probability of that parameter within some finite range, because typically you can only calculate in a finite range. Although you don't have to do that. It can be some like Gaussian or something that goes to an infinite range. But you have to choose something, and it's always a non-trivial choice, even though people sometimes they try to make as uninformed of a prior as possible. Every choice is non-trivial and not equivalent to the other. So a uniform probability for alpha, the strong coupling constant, is not the same as uniform probability for G, because alpha is G squared. And so whatever you choose can be important. It also cannot be important. If you make a very broad prior, but like the posterior ends up being like a super narrow peak, then it won't really matter which broad prior you chose. But sometimes it can really matter. Sorry. Mm-hmm. Mm-hmm. Well, it depends on the context whether it leads to different results. So, but in principle, yes, it can matter. Mm-hmm. 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 It depends. It depends on the analysis. So in many cases, yes. I don't know if I should jump ahead. Oh, yeah, not too far ahead. Well, these are all constrained. Do I have a better example? But I mean, yeah, I guess this is a bad example. But in other cases, for example, at some high temperature, the prior is the same as the posterior, so you really didn't get any information from the data. And so if you chose a different prior, it would change a lot. It would probably just match the prior. Whereas if you have a case where it's like really narrow, which I don't think I can see in, I don't know. So if you have a really narrow distribution, then it doesn't matter as much. It only matters what the shape of the prior is within that posterior. But if it's very narrow, then it's not going to matter. So it's really context dependent how important this issue is. But I do want to emphasize that it is an issue that's always there, and there's no completely uninformed neutral choice. Like any choice is a choice for the prior, and you have to pay attention to whether it matters or whether making a different choice would have given you a different result. Yes. Mhm, mhm, mm. Sure. Yeah. So if you have better and better constraints, you're saying then the prior depends less. Yeah. Yeah. Compared to what? It's certainly if it's close to if the prior is close to the posterior, then we have gained not very much information. Yeah. The situation right now. I'd say that you know, many of these very broad posteriors are because we're trying to be as robust as possible. I mean, so there are different results. People have done ones where they put in a lot of extra data that might depend on things that aren't in the model. So it's less robust, but they get very narrow results. So I think it's a bit conservative why we have very broad results. But in general, um, I mean, I think it's clear that we have information, and it's kind of up to you whether you think, the uncertainty band is too broad for us to. It's so broad that you don't really think it's worthwhile or not. Yeah. Well, almost all the ones that I've seen, zero is actually not compatible. But I can say things like we checked whether how much you can say about the temperature dependence, and um, basically there's no evidence of a non-trivial temperature dependence. So you see all of this stuff, but if you enforce a constant, that also reduces the number of parameters. So you have to take that into account when, I mean, you're always going to improve the fit when you add parameters. So there's a way in this framework to take that into account and say whether the increase in fit is justified by the extra parameters. And yeah, so at least in this particular analysis, having a constant in temperature is not ruled out. Is just as but we definitely can rule out zero. Yes, there was one back there too, but I don't know. I don't know who should go first. So, I mean, my personal perspective is we are learning more and more and gaining more and more confidence about our knowledge of these things. But whether that's good or whether it's good enough for you is up to you, our current knowledge. But I think we have more knowledge than we had in the past, and we will have more in the future. We're moving in the right direction.
Is it because this is especially suitable to be applied in heavy ion conditions, or is it because, what is the reason why, for instance, this method that uses Bayesian inference and not, let's say, a standard fit, like, maximum likelihood?
But what do you get from a standard fit?
Those that are used in hydrophysics, the frequency approach. So you just write a likelihood with the parameters, and then you try to maximize it. So why the Bayes theorem and not another method?
I mean, my answer is just that I think it's a very good framework for having a very detailed treatment of the uncertainty. You have a lot of information about the uncertainty, about degeneracies. So if I change this parameter, can I accommodate that with other parameters? There's lots of correlations in this. You end up with however many parameters you have that many dimensional probability distribution to describe that, and there's a lot of information about that uncertainty, which I haven't seen anything similar to that in a different approach where you have such detailed information about uncertainties. So for me, it's just a good way to treat uncertainties. It's nothing magic about it.
Let's say you get a probability distribution, more like but only high values are bad.
Yeah. Sure. I mean, it's this normalization factor here. So so when you make these plots of like these relative distributions, so it's not really in any of these plots, but the information is still there, and it's important to do that. I mean, you should always then go back and compare like how well is your model fitting the data in general. Like if all the fits are bad, this only shows you the relative value given your model. What's the relative probability of different parameters? And yeah, it's an extra step, but it's all contained in these analyses, and it's an important part. Yeah. Yes, because of the prior. So that's what I was saying before. Like we don't actually have compelling evidence from the observables that we use to constrain this that you have any temperature dependence. So this shape, I mean, yeah, this shape is kind of inherited from the prior, right? Mm-hmm. Although we're getting a little ahead of ourselves, but I wonder if I should. Let's see. Where was I? Oh yeah. So the context of the results I'm going to show is this particular analysis, which I've already been showing, but let's introduce it anyway. Yeah. So I wanted to just emphasize, yeah, that the result, and yeah, as Gabrielle said, that's not all of the results, but like one of the main results is this posterior probability distribution, which yeah tells you how likely different points in parameter space are and all the correlations and everything. And so in this particular case, it's a 17 or 18 dimensional distribution. So it's generally hard to visualize. So I showed that just to say like what we usually have to choose things to look at, right? So the most obvious is you marginalize over all but one of the parameters, or you project onto that one parameter, and that's I know you can't see any of this, but this is just explaining what what it means. So these diagonals on these corner plots are always these one-dimensional marginalized distributions. So if I don't know anything about all the other parameters, I'm just projecting onto that one, then it can have this. And then you look at correlations, usually pairwise, because again, having more dimensions is harder. So these are like marginalized over all but two, and then all possible pairings are what you're showing in these corner plots. Yeah. Yes. In this particular analysis, it's let's just skip ahead because I have this shown. So we have these two slides. So we've got mean transverse momentum versus centrality for three different identified particles, pions, kaons, and protons. We have the yields and the transverse energy of, so the all charged hadrons transverse energy, and then the identified pions, kaon, proton yields versus centrality. And then over here are these flow coefficients, two particle cumulants for second, third, and fourth harmonic. And then this is the variance of the mean transverse momentum event by event over centrality. So I don't know if I counted how many points there are, but you get some idea. That's how many. But it's actually intentionally restricted. So I think, going back to that question, like we didn't include a bunch of highly detailed momentum dependent observables because we thought that they would be sensitive to things that we're not studying here, in particular viscous corrections to the distribution function when you switch from fluid to particles at the end. And so to get a more robust, but again, wider and more conservative result for like viscosities. So you can definitely add a lot more, and people have added more deep observables, but this analysis was these, if that answers what you wanted to know. Yeah, but it really depends on the context, right? Some parameter, I mean, there are a lot of things you just can't do with any of the parameters, and so it's really context dependent of the observables. And in some sense, adding more parameters can give you a more reliable result because you are marginalizing over more uncertainties. So it's not always the best to just have a model with the fewest parameters and then see if I can fit data, because it still might not be the right model even if you fit the data that you're looking for. So it's more tricky how many parameters you want to add, and sometimes it's good to add lots of parameters because then you get a more reliable result if those truly represent some things that you're uncertain about, which in this case, yeah, there's lots and lots of uncertainty in what's the correct description. So this is going to be the context. Yeah, so you can do it like this. I'll also show it in this way, but I'll come back to the results later. And these are the parameters, which we can also discuss if you have anything. And then finally, let's get to causality. So the main idea of these results are going to be, so this was actually done back in 2021, but the new results then are going to be asking how does this change if we take into account the fact that sometimes these simulations are solving the hydrodynamic equations when they're in an acausal regime. And I want to know, how are these results effective if we include that information and we, for example, don't allow hydrodynamics, don't allow the model to be used in those regimes. Yeah. Why is this happening? For a few reasons, which we'll get into. I mean, a big one is the system is driven far from equilibrium at early times. But also, you'll see some points in some parameters are not physically possible. So there's different. I think maybe we should discuss that as we go, once we see. Yeah, yeah. Mm-hmm. Okay. Yeah, to 60% confidence. Mhm. Mhm. Probably. Mhm. Who knows? It's true within the context of this model and everything that's all the parameters that are in this model, the way it's treated. Then this is true. But if there's something wrong with the model, which there probably is, then it's not necessarily true. So yeah, so that's an example. So yeah, I'm going way out of order, but so a lot of this is due to how this is parameterized. So this 8 over s we just take as being this piecewise linear with one kink, which so normally it should be a minimum, but we took the sort of agnostic approach and allowed the slopes to be either positive or negative just to see if the data would tell us that is the minimum, or if the data cannot tell us that. But yeah, so the parameters are the values here, and then these slopes. But that means that there's correlations in temperature. So if in reality the viscosity is really well constrained right here, the posterior will still be well constrained out here just because the slope was constrained. So part of this, so this is related to what Chun was saying. So we generally don't even use the fluid below 150 MeV or whatever the switching temperature is. There's a whole prior for that. And so we're literally not using any information at 100 MeV. It's just inherited from the slope up here. I think so, yeah, probably. But so yeah, there's it can be, yes. The more direct result is the posterior for these particular parameters. But even then, that still relies on the fact that you have this parameterization, which there's no reason to think it's realistic. It's just, you know. Mhm. Let's try to go back. Where were we? Okay. Okay, should I go on to causality? I don't know. I said we have lots of time, but no, I'm not. But I mean, I think this the main point I think is to discuss these. Like, I think the results are actually less important than the discussion along the way, so it doesn't really matter. Um, so yeah, the hydro that's used in the in this analysis, and also really in the majority, I think the vast majority of uh, uh, you know simulation analyses in heavy ion collisions is some Israel-Stewart type equations. Looks something like that. So yeah, so first we parameterize the shear and bulk viscosity in some way like this. Each of them has like 4 parameters or so. But then, okay, yeah, I can. So at low enough, let's see, at high temperatures, definitely it should go to 0. And then at low temperatures, does it necessarily go to 0? What does it do? It may not be exactly zero, but you do expect kind of a peak, like the largest value near the transition. I don't know whether it should necessarily go to zero.
There's a note by Guy
Mhm.
studying the about viscosity of the time, and it was exponential.
It goes up.
All the way up. Not the viscosity, but the viscosity over there.
Yeah. So that's, yeah, but that's probably below here, below 100 MeV.
But then, so below temperature has to go exponentially higher up, and so that means that we're going to be higher. Thanks.
But it, but I can say we're not sensitive. I mean, we don't even use this because we do switch to a kinetic description, somewhere around here. So the parameterization down here shouldn't matter. But I just wanted to say, okay, there's lots of other coefficients that we need. So these are typically just chosen by Gabrielle, let's say, and everyone copies. And all of this actually is going to, this matters. So these results are going to be kind of, specific to this context. How did we parameterize? So we take these relaxation times to be proportional to the shear and bulk viscosity, and then we take all these other terms to be proportional to those parameters. So, and with all these fixed, the exception being these relaxation times, which sometimes are varied. So in our analysis, it's going to be this one, but I'll show some results with both of these varied. Yeah. No. So that's what I'll show. So really the ones that typically have the largest effect are these relaxation times. Yeah. Well, I mean, just more important than the others, let's say. Whether it's still probably it's not really very important. They don't have a big effect in most cases. I'll only show like heavy ions, so lead-lead collisions. I'm not talking about like really small systems. So there can be lots of places to look for these effects, but in general, it's not a big. Yeah, even if you switch them off completely. That guy. It's a calculate. I don't know. You can explain. Yeah, this is like a very simple kinetic. I mean, it is from kinetic theory. It is from a particular kinetic theory. It's not a general result from any kinetic theory. It's just something like that. Yeah. Yes. Okay. So then I just wanted to highlight. Okay. For causality, it's probably obvious that these relaxation times are going to be important because this tells you this is a characteristic time over which these viscous components relax to some particular value given by these constitutive relations. Yeah. This one? Here. It will be yes. Why does it depend on CS squared? You mean put in a value? Yeah.
But I mean, the problem, I guess, is that you can that's the data is very sensitive to details of this guy. So up to now, I guess people just read the number of values. But again, there's no good reason to exactly what the data is. The question is, why don't we just
Is that better? I mean, it's still a choice, right? I mean, you're not really removing having to choose a value. It's just a different value. Is it better than these? The ones that go here, yeah.
I have a question. So forgive my ignorance, but I didn't know that your simulation went to, so it includes quadratic terms. So you have phi sigma and phi pi. So these are newest including quadratic terms.
Yeah,
Right.
I think so.
So, but of course, then you have, in the simulation that the quadratic terms in terms of velocity. Yes. So it may have an influence because of this order. So you need the acceleration squared and the squared. It's like a comment that the problem is that these terms are just so essentially we get a rate expansion. But you cannot solve a rate expansion. So what some people do like we sum some of these terms as you get sigma squared, if you have pi sigma, similar now, you have sigma dot, you get a pi dot, you get so on. But this what this is squared so far, you have the way to resolve it to form. But the fact is, you can just put this for this equation, it doesn't allow it goes out. It's written there. The line is common. If you open the book, you can see the line going up and down. But if you don't open it down, it goes out. These are stable. And this is exactly what is formulated. It should be there. It should be there. That's I should say that it kind of is.
I think we should probably move on. We can continue this discussion because yeah, we'll try to get through some slides at least. Because yeah, I'm actually starting now. Okay, with linear causality. So this is very simple. So we just take a static global equilibrium system, take an infinitesimal perturbation, and look how it evolves. So you can linearize the equations of motion, and if you demand causal propagation, then you get a fairly simple inequality that has to be satisfied. And just reminding you of the particular parameterizations that we use actually simplifies this. So everything kind of cancels out, and these are just constants, and this depends on temperature. But we can just take the worst value of CS squared at the near the transition in the lattice QCD to just give like values that these coefficients need to have. And so here's an example of one of these Bayesian analyses, not the one that I'm going to be using, but they've varied both the shear and bulk relaxation times. And this full rectangle is their full prior, so it's uniform within this prior. But you can see that actually some part of their prior doesn't satisfy even this. Which is, I mean, so it's kind of the minimal that you expect, I think. Like if you're infinitesimally close to equilibrium, if your theory has any hydrodynamic regime at all, hydrodynamics should work, and so it should have values that are within this. Yeah. There's only one. There's only one in the linear. It becomes bigger than one. Yeah, positive. Yeah, I don't think it's possible. So I take the minimum CS squared because, I mean, any simulation travels through that temperature at some point. So, yeah, so just simply, so this is actually the one that I hopefully will show results for, where only the shear relaxation time is varied, but even this one you can see violates it because he kind of forgot that the bulk term was here. So the prior was taken assuming the bulk wasn't there. And then, so MAP, this is the maximum a posteriori point in parameter space, which is a thing that's often reported. So it's the most likely point in parameter space. But also, I always like to warn people that it can often be misleading because the distribution can be extremely wide and flat in various directions. And so people often take too much information away from this, saying, okay, parameter has to be here, when actually we have basically no information about that parameter, and the algorithm just kind of found a maximum as best it could. So that's why I show, so these green points are random. There are 20 random samples of the posterior in this other analysis, because that's what I could get access to. And so it's not just the prior. You can see that lots of the posterior is also in this bad regime. So that's kind of interesting. But as far as like observable effects, if we had taken a better prior, it wouldn't really change anything in practice because the observables don't really depend hardly at all on these relaxation times. And so there would be no effect on the actual conclusions. So it's kind of just a interesting fact. So more non-trivial is causality in a general case. For it, you just have a general system and a general condition. The hydrodynamic equations can be acausal, so these are necessary conditions for causality. So if they're broken, then you are not in a causal regime. So there's 6 of these. So I'm using the same notation from Chun on Monday. You write all these things that have to be non-negative. But in this particular case, the 6th one is most important. Although, as Chun showed the other day, if you use a different parameterization of the shear relaxation time, then some other ones can be more important. So it is kind of specific to the way we do things currently. Anything else? No. So let's check this. Let's see if we can. So we saw on Monday already that it's not uncommon for the simulations to have some enter into a causal regime. And what I want to emphasize here basically is that typically it's worst at early times. So you have this very high energy collision system, these Lorentz contracted pancakes hit each other, and then at the very early times, you have very strong longitudinal expansion that really tends to drive the system out of equilibrium. And so that's where these problems tend to be the worst. So these depend on temperature via the CS squared, but they also depend on local conditions based on the bulk values of the bulk pressure and values of the shear tensor. And these coefficients, which can depend on temperature, except we chose parameterizations where the ratio is constant. But so it depends on local conditions in somewhat complicated ways. The red point, yeah. So this is just checking, just doing a full simulation and checking locally in each fluid cell whether any of these necessary conditions are violated. And if any of them are violated, then you get the red color. Yeah, so I have different times here. So you can see it gets better with time, which is the only real purpose, because I want to motivate what I want to do. So okay, so here's this actual jetscape analysis. Now we just the one that was originally done without any reference to causality. Here is the posterior distribution. So this is how much of parameter space has a certain amount of acausality, which we quantify in the following way. So we just take one single simulation at each point in parameter space, zero impact parameter, and then we quantify how much of the system is in an acausal regime. We define by the total energy. See lots of typos here. So what fraction of the energy is in an acausal regime? And this tells you like how often it happens in parameter space. It's the parameter posterior. So for example, you can see there's a little blip here. So there's some parameter values where if you run a simulation, the entire system at the earliest time, onset of hydrodynamics, is in an acausal regime. But typically it's some fraction smaller than 100%. And so yeah, you can see here's some numbers about if you cut out how much probability are you cutting out if you take cuts to the right of different lines. So you can see that even if you cut out basically everything, you don't allow any acausality, there is still some parameter space left. And we want to know, what does that parameter space look like? How much is this changing our conclusions if we make certain cuts? If we cut out everything to the right of this green line or this black line or so on. This is the posterior. So this is after comparing to data. This is but in the original analysis where we don't take into account anything about causality. It doesn't matter. I mean, these things commute. You're multiplying the prior by the likelihood. Setting the prior to 0 is equal to setting the likelihood to 0. You're just multiplying them together. It doesn't matter whether you check before or after. Some point in parameter space is associated with some amount of acausality. It doesn't matter whether you've compared to data or not. But this tells you of the data that's preferred, of the parameters that are preferred by experimental measurements, this is how bad the acausality is. It could be worse in ones that don't fit data at all, but these are the ones that do fit the data. So yeah, what happens if we make cuts on this posterior? Or maybe a better way of thinking about it is if we put cuts on the prior. We set the prior probability to 0 when there's too much acausality, or any at all for the strongest cut. So just jumping straight to the observables. So this is the maximum a posteriori point. So this is the very best fit that you can get, as defined by this overall likelihood function that we showed before. So this, and so you probably can't really see anything. So I'll just show you that. So you definitely have not completely destroyed your ability to fit data. It's kind of still looks okay, but there are differences, and so it does hurt. So let's say this maximum a posteriori of the original posterior is about 3 times as likely as the best fit after the strongest cut. So if you think of like a Gaussian or something, this is more than 1 sigma away. Of course, it's not a Gaussian, but roughly speaking, that's how you think about these things. Yeah, so that's kind of, so even though like it's very, very common to have a causality, if you say, I don't want it, it's still, we can still do things. It doesn't, it's not essential to our description of a heavy ion collision. Yeah. Which one? This one? Okay, so yeah, I probably didn't explain it correctly. So let's see. I did all of this, and so this is comparing the best fit, the maximum of the full posterior without any cuts, to this cut down here where we say 0.0001% is the maximum energy fraction that we allow to be acausal, which is basically numerical 0. All of this is a very rough estimate. So we're only doing one event. We're only doing it right at the onset of hydrodynamics. We're not comparing all events, all centralities, all through space-time. We're just trying to get a rough idea. So we removed 93.5% of the posterior parameter space. And then within that reduced space, we find what's the most probable point, which is the best fit to data. And this is what you get. The colored ones were the original, and then the aqua are the slightly worse fit. Which one? Oh, the higher ones? I don't, but it's a very good question to ask because this really depends on how we parameterize these things. I don't know if I can. Oops, where did we have causality? Well, I mean, my answer is right now I don't. But it's a good idea to stare at this and figure out if we made different choices. Mm-hmm. So it's a sort of thing that we should study like in simulations, but this full Bayesian analysis was done using a particular model. And so if we want to analyze that posterior, we can only work within what was there. Yeah. 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 So I'm not showing the full band because it's pretty narrow. So I wanted to be able to show the difference, even though you probably can't see that either. Mm-hmm. It doesn't. It changes about this much. Yes. I know it's not shown here, but the distribution doesn't change very much. So let's, yeah, so we can just look at other, so the most obvious thing that matters is the shear relaxation time. So this is actually showing the posterior before the cuts. So this is what's showing you that it's basically flat. So the data don't tell us anything about this, and that's because this shear relaxation time really doesn't have any effect on observables. Yeah, the prior was completely uniform between, I think 2 and 8, whatever I showed earlier. Yeah, and the data doesn't give you any extra information because it's really just such a small dependence of observables on this. But causality, of course, does. So if I put sequentially like stronger and stronger cuts, like maybe I allow 1% of the system initially to be in an acausal regime because it probably doesn't matter much if it's at the edges, or 0.1%, or the stronger one. This is what happens. So it's the obvious one is, of course, you can't have a too small relaxation time, which you can see already from these linearized analyses. If it's too small, things will propagate faster than light. But it's interesting that the nonlinear conditions actually tell you that it can't be too big either. So that cuts out both, and you actually have a smaller range that's allowed. So as far as things that actually matter physically, here's the maximum value of this Cauchy distribution for the bulk viscosity versus temperature, which yeah, actually gets shifted a bit to the smaller values if you put these causality cuts on there. So looking at it in terms of temperature dependence, yeah, the shear viscosity doesn't really have too much of an effect, but the bulk viscosity, actually the preferred value shifts down a bit. So values that you thought were compatible with data before become incompatible if you disallow these parts of the model where you have acausal simulations. So I think this is a good time just to end the talk, and yeah, that's about it. So hydrodynamic simulations, you know, acausality is an issue in these. It happens, and demanding limits on acausality does not destroy our ability to analyze data. It's not like a complete disaster, but it does have non-negligible effects, especially when we're doing all these sort of precision analyses where we're trying to get precise values for parameters. It's something that's important, and so we should be worrying about it and improving our models. So, thank you.
Equation.
Just show the equations, or
Quadratic terms, yes. So the question is, if you remove all those terms, delta pi pi, pi 7, pi pi pi, and so on, how would this impact the distribution parameters?
set them to 0.
Yeah. So suppose you have so I have equations where all the known linear terms, like delta pi pi, delta lambda pi, pi pi, and so on, removed to get 0. Okay, so you don't have pi mu sigma mu, you don't have pi mu theta, and so on. So the question is, perhaps to large orders, what would happen?
Yeah, so I mean, Gabrielle could comment again on the instability, but in general, every study I've seen that just varies the values of any of these parameters sees a very, very, very small effect on typical observables in heavy ions. So typically it doesn't matter, but with the exception that I guess if you set them completely to 0, then things can become unstable. Is that right? Did you say that, Gabrielle? One of, you said, this one? Yeah. Or,
they want to have. But it's not exactly the same. The fact that they have on data, the question is the one duration, if they don't by 5, or they multiply by 10. You'll see a small one.
Yeah, it's still small, but yeah.
That if I include, for instance, okay, if I include a rotation square, then this will become okay. But if you, yeah, first of all, so that's it. So technically, I don't even know how to do such a because for me, it's a little bit of time. I don't know how to solve, and I don't know how to solve other ranges of that. Now, what people sometimes do in this code is just estimate the time of the like the previous time. Yes. And then if I do the development, sometimes work, then put the ranges up there. The code. So this doesn't know how to figure out the so that said they will come back to the top 5. But I don't think that is looking for those questions. I think that the problem is that it goes to a direction that even a software piece of and you see the queue doesn't have. Yeah. So it's a different type of figure. Not sure when you were saying to generate 275. Well, but in equilibrium they survive. Right? In equilibrium, yeah, the problem is that the equilibrium they survive. Yeah. So maybe you have area conditions which you need to be the initial order randomly. Yeah, and if the system will hold the equilibrium up to the very end. I agree with you. So maybe the negative is really sparse. Usually, when we have a variable finding, it's related to the use this remove this kind of basically by a 5. Right. Kind of construct model that use the rate expansion. Yeah. That's the tricky for you to use. So for omega square, I can find a variable field that would basically make the kind of make a causal version of the equation that you can use. No, yeah, I understand. It's a conceptual difference. There is an equation.
I have a technical question about the hydrosimulation. When your procedure is LS and ZLS. So how do you input this information in your hydrocode? I mean, because when you calculate the temperature, it's going to cells by cells. So this means that each cell you have different transport direction.
Yeah. So you just, yeah, I mean, they just appear in the equation. They're right here. So in every cell, you find the local temperature, and that gives you the value for wherever they are. Yeah, zeta and eta in that cell, and you just plug those into the evolution equation to get the next time step. So I'm not sure there's anything non-trivial about that. Other people can comment if there's something I'm missing. No, I think it's quite natural for a fluid to have transport coefficients that depend on things like temperature. I mean, They all do. Even a conformal one has eta proportional to S, or temperature, or temperature to the fourth or whatever. Yeah. So it almost has to depend on temperature. It'd be very strange for it to be a constant, I would say. Yeah. Or, sorry. So BDNK. Yeah.
So I'm just wondering, so this whole machinery, right, huge. Why don't we that approach avoid any causality problems whatsoever, or is it too naive?
No, it's I think it's people are writing it into codes, and I don't think it's automatically a better theory. So you never have this problem, but you could almost think of it as a good thing. When this thing is entering an acausal regime, perhaps that's telling you that you're entering a place where hydrodynamics shouldn't be applied. So I think there's different ways of looking at it. So I think it's definitely good to use these equations and compare and see what happens. But I'm not sure everyone should just replace everything they're doing with BDNK. I don't think that's the right takeaway message. But using them both and comparing them is a great idea. Yeah. So then you have no idea when it's valid and when it's not valid. It's just always causal and it always runs. But it may or may not be a good description of the underlying QCD system. Oh yeah. Okay. It's the difference when we put cuts in. This parameter or the temperature dependence? Temperature dependence? Sure. Yes. That's my main goal in this, is to tell people we need to improve the theory, not to say that, okay, this aqua result is the correct value for QCD and you should take it away. It's more to quantify how big the problem is, so to motivate improvements. I'm never sure of what what a reader will take away. Mhm. Yes, you should always be worried about this, and it is, the job of the author to dispel any notions as best you can, but you can't always control these things as well as you would like. Misconceptions. Yeah.
But if that is a lot for this analysis,
Mhm.
I think that there are many problems. But we can't see the problem like how it is here. Very likely.
Right. Even more with this particular analysis, we're only directly constraining tau pi and the initial condition because we're only looking at the initial time step. So we're not even sensitive directly to these actually. So this is an indirect constraint here. So the initial condition was constrained to be a certain thing, and that means that too large of a bulk will not be compatible with data when used with that initial condition. So it's complicated, and I would say the first thing we should be doing is looking at what we're using for the initial stages, since that's a little bit crude, and we can do better there. Before just replacing Israel Stewart, I think that's a good place to start. Mhm. Okay, so there are a bunch of conditions that are sufficient for causality and a bunch of conditions that are necessary for causality. And so unknown means it's in between. So it has the sufficient conditions for causality, but it doesn't have the necessary conditions. And so then you don't know for sure whether it's causal or not. So I mean, so yeah, we just don't know. It's just unknown.
Very simple. This is a 2 plus 1D or 3 plus 1D.
This one is 2D, 2 plus 1D.
Everything you show.
I think so, yes. This is the whole system except they put a cut on where a typical freeze-out temperature is, and then marked everything else black because then nothing that happens at lower densities really matters. This thing just expands. So this is everything of the whole system inside the whole lead collision system within the freeze-out surface. Yeah, so at early times, yeah, kind of the entire edge is acausal for this event in these parameter set. Okay. So the continuum limit of what we're solving on the computer is not the equations that I showed? That's your statement? Yes. Ah, okay. I think this exists in these. This is this related to this flux limiter, Gabrielle? That it controls, yeah, how much artificial viscosity you have to. So I think if you set that correctly, it should be okay. But of course, we don't. I mean, it's just a fixed value in the whole simulation. So in principle, what you're saying is correct, but I mean, we're only checking causality of these equations. So if we're not solving these equations, then it might not quite be correct, but they should. They should. Yeah, I can't promise that it does in exactly the way that we do everything, but I think with the algorithm it should if you choose the flux parameter correctly, like
Theoretically, imagine that you're just solving the math. Then the code, we have verified that when you are in outside terminal stable, you are stable, the code is still stable, the code is not solving the math. When you are in the causality, at least some of the causality. So yeah, in general, there will be some discrepancy between what the code predicts and what the math predicts. Is this the question? Yes. There is some difference, but you wouldn't like it. I mean, you know well, right? There's an imperfection of the code, but you would like the code to reproduce the partial imperfection.
yeah, and I mean, at least in normal regimes, these things are carefully well tested that they've very closely solved the correct equations. So I'm not sure this is a big issue. I think checking whether the equations are acausal is a good way to tell you whether the theory is in a good regime or not.